Dear colleagues, I'm very honored and excited to give this award lecture today. My name is Tanja Stadler. I'm an associate professor at ETH Zurich. My group is developing new statistical and computational tools in order to answer evolutionary questions. Over the past 1.5 years, we were in particular focusing on furthering our understanding of SARS-CoV-2 spread. And today I want to give you insights into what do SARS-CoV-2 genomes tell us about the pandemic spread. I will first talk about general dynamics of the COVID-19 pandemic, followed by focusing on heterogeneity in the host as well as pathogen population. And finally, I'll conclude with some remarks. First, the general dynamics. In epidemiology, the reproductive number R is a key quantity. R is defined as the expected number of secondary infections at a particular time in the epidemic. So if one person on average today infects 2 people, and then those 2 people again on average infect 2 people, the reproductive number would be 2. Why is R so central? If the reproductive number is bigger than 1, that means the epidemic is growing exponentially. It is doubling in size in constant time intervals. If R is smaller than 1, the epidemic is declining. However, the R value not only tells us something about the dynamics as of today, so how is the epidemic unfolding, it provides further information, in particular through the basic reproductive number R0, which is the R value at the start of an epidemic before we had any interventions or immunity in the population. And now, based on simple but very powerful epidemiological models, one can derive that 1 minus 1 divided by R0 of a population needs to be immune such that the pathogen cannot spread widely, meaning such that the R value at that particular point in time is below 1. Thus, at the start of the COVID-19 pandemic, it was of crucial importance to understand what is the R0 for COVID-19. Let's go back more than 1.5 years ago and look at the outbreak in Wuhan. Julia Riot and Christian Althaus, colleagues from the University of Bern here in Switzerland, looked at confirmed case data very early from Wuhan. And they essentially tracked how fast are the number of confirmed cases over time increasing. And so if first you have 10 confirmed cases and in the next generation 20 confirmed cases, then 40, then 80, we would double with every generation. That would mean an R0 of 2. And indeed they estimate that the R0 was around 2, however with a rather large uncertainty. Now the big question was, we knew in Wuhan this pathogen is spreading very fast. What is the R0 at the start of the outbreaks around the world? It could be that different climatic conditions, different cultural behaviors, etc., induce a higher or lower R0 for other parts of the world. Now, when aiming at estimating R0 for non-Wuhan outbreaks, we actually need a different approach from merely looking at how fast number of cases increase, as early case numbers may either be actual local transmission or will be additional introduction events from Wuhan. And introductions will be biased the R0 upward if not taking them into account. I want to now convince you that sequencing data actually allows us to estimate the R0 in an unbiased way by reconstructing local transmission clusters for which we then quantify are not using phylogenetic methods. What is the idea? The SARS-CoV-2 genome changes through mutations. So imagine at the start, the first infected individual was infected by a virus which had 8 nucleotides. Here ACACACTT. Now this horizontal line would be the first infected individual, which then transmits to a second individual. And in both individuals, obviously the virus is replicating, and in the first individual, at some stage, it mutates from a C to a G on the 4th position, while in the second individual, it mutates from a T to a C on the 7th position. And further downstream, we would see additional transmission events as well as mutation events. Now, of course, we don't know this past transmission chain. However, we can sequence the virus of infected individuals as they show up at a testing center. And then, based on similarity of the genomes, we can actually reconstruct a proxy of the past transmission chain. That is what is being done around the world since the start of the pandemic. Here I bring you an early SARS-CoV-2 tree which we reconstructed in my group, focusing on the outbreak in Wuhan, the province Hubei, here indicated in red, and then downstream spread into Europe. And now you see, for example, in the top right, all those bluely colored sequences. Those would be all French sequences. And so we know this is a French outbreak. There's no further introduction. So we can analyze for that outbreak what is the basic reproductive number. And if we make the tree larger, we would see several of those, say, French outbreaks. And so we would have several outbreaks based on which we can estimate the reproductive number. So what we were doing in early February 2020, we selected, based on sequencing data, outbreaks from different countries to quantify the basic reproductive number. First, that was obviously only China, but as we all know, soon we could add more outbreaks as the virus was spreading. And here I show you the basic reproductive number, which we were, the estimates we were releasing at the end of February 2020 for China, Italy, so the outbreak which then spilled over to the rest of Europe, Washington State in the US, as well as a cruise ship, the Diamond Princess, and in purple, the prior distribution, where you see that was quite different from the posterior, where we estimate for the countries and larger regions a reproductive number around 3, for the cruise ship a bit higher, which makes sense that people were in closer contact there. Now it's thought to be that the basic reproductive number back then really was 3 or even higher than 3. And what does that mean? An R0 around 3 means that we need 66% of the population to be immune, such that the virus cannot spread widely anymore. And in particular, based on those studies which we released late February, we were expecting and quite sure that the spread across the world would be very similar to the spread we have seen in Wuhan in the absence of any interventions. Now, what happened since then? We were closely monitoring the reproductive number of the COVID-19 epidemic through time across different countries. And how do we calculate the reproductive number? We look at the number of confirmed cases on each day, or alternatively, the number of hospitalization or the number of deaths. And from that, we calculate the reproductive number as follows. First, we assume that a person transmits roughly 5 days after they have become infected. So say here in my cartoon example, which are actually the confirmed cases from Switzerland, on April 8th, we had roughly 700 confirmed cases, while on April 3rd, we had 1,000 confirmed cases. So 1,000 people infected 700, meaning the reproductive number would be 0.7. Now, the people who were confirmed on April 8th did not get infected though on April 8th. At that time, roughly a person was reflected in the statistics 10 days after they actually were newly infected. So the reproductive number would be 0.7 10 days earlier, namely the 29th of March. Now, those 5 days and 10 days are obviously not fixed numbers, but there's uncertainty around. So when we calculate the R value, the reproductive number, we in fact take into account distributions for the time until a person transmits the virus onwards, as well as the delay distribution between infection and confirmation. And due to all those uncertainties, we then also get uncertainties with the reproductive number, here being the shaded region through time. Our core calculations are based on an R package epi-estimate by Corey et al., where we then put around all those uncertainties which we know for COVID-19 to in fact obtain reproductive numbers, taking those uncertainties into account. Those reproductive numbers are displayed on a dashboard for more than 170 countries. Here, for example, I show you Switzerland, the UK and the US, and you can see how the reproductive number from March to May developed for those 3 countries. Together with the reproductive number, you can see the underlying core data, the number of confirmed cases, together with what is shown at the very bottom in solid lines, the stringency index, so how stringent interventions were, as well as the vaccine coverage, which are those dashed lines. If you want to get a quick overview, you can also just on this dashboard look at the map to see the darker red, the higher the R values. So far, I talked about general dynamics of the epidemic in a particular country, and now we want to switch and actually take into account and appreciate the large amount of heterogeneity which is actually in the host population as well as in the pathogen population. In order to assess the heterogeneity, sequencing data is a core information. Due to that, we actually started in March 2020, so just when the epidemic took off in Switzerland, a sequencing consortium, the Swiss SARS-CoV-2 Sequencing Consortium, where we sequence every week samples from all across of Switzerland. By now, we published around 25,000 sequences, which are available for researchers around the world and authorities to explore. This is almost 75% of all available SARS-CoV-2 genomes on GIS8. What are we now doing with those sequences? So first we can, based on similarity of genomes, reconstruct a tree, the SARS-CoV-2 phylogeny here for Swiss sequences, and colors, say in different colors, different variants of the virus. And when zooming into the tree, we can start exploring which countries have a lot of exchange of virus. For example, here you see Swiss sequences together with sequences from the US, Greece, and the Netherlands. When looking at those trees, you should always be very careful to not draw too many conclusions directly, because what you see may be biased based on which sequences you include. For example, the UK is sequencing much more than any other country. So often you would see UK sequences with the country of your interest just because there are more UK sequences. However, if you do an appropriate subsampling, zooming into those trees can give you some information where there is a viral exchange between different countries. Second, we use our sequencing data together with sequencing data made available globally to investigate SARS-CoV-2 evolution. In particular, we're interested in detecting and characterizing new SARS-CoV-2 variants with altered characteristics. So in here one should say SARS-CoV-2 is changing roughly every 2 weeks, so new variants or new mutants are coming up all the time. However, what we really are interested in, when does SARS-CoV-2 change its properties? And in particular, what's of core interest is to detect variants of concern as defined by the WHO, which are variants which either have a higher transmissibility compared to the currently circulating strains, or cause a more severe disease outcome, or have some immune escape in the case of people who had a previous SARS-CoV-2 infection with the common variants or were vaccinated. Throughout 2020, we investigated and explored if we see any worrying new variants, any variants of concern in Switzerland, but also across Europe. And so over summer 2020, all of a sudden, we saw that this orange variant is increasing in frequency quite rapidly. So while it was not present at all in July, it was actually by end of August giving rise to more than half of all infections in Switzerland. What we then did was we compared the dynamics of the different variants across Europe. And what we saw, this orange variant with a proper name being 20A.EU1, was actually dominant in Spain. It emerged there in late May, early June, and became was the dominant strain since then. Also in the UK it was dominant. In the Netherlands it became dominant. However, in other countries it seemed to have not been able to take off. Say in Belgium it didn't really take off. In Norway it took off, but then other variants took over. So this was a first sign that not necessarily is this orange variant, so 20A.EU1, really more transmissible. However, this was comparative, looking at the frequency evolution through time. What we then really wanted to see is if the second wave, the fall wave in Europe, was driven by this variant 20A.EU1. So we used SARS-CoV-2 genome data to calculate with phylogenetic methods, which in my group we developed for the past few years and which are all available in the software package Beast2. We estimated the reproductive number through time for 20A.EU1 and for all the other strains which are not 20A.EU1. And what did we see? Essentially, over summer, the non-20A.EU1 variants had a reproductive number of 1 or below. For 20A.EU1, there was first very big uncertainty. And then starting September, both variants were significantly below 1 with their reproductive numbers. So there was a decline in the epidemic. And then actually both variants had similar patterns. So the reproductive number increased first in October and then again towards Christmas. So what we see for Switzerland, the fall and winter dynamics were not driven by the new variant. So it suggested really that 20A.EU1 doesn't have higher transmissibility compared to the co-circulating strains, as already suggested by comparing the frequencies of 20A.EU1 across the different European countries. So we concluded that 20A.EU1 is not a variant of concern due to having a higher transmissibility. In fact, then exploring further what caused the initial growth of 20A-EU1 in Spain, it was shown that through epidemiological data that this variant was first connected with a number of super spreading events back in Spain, and then there was a lot of summer travel from Switzerland and UK into Spain, and so holiday people most likely brought this virus back, interacted then in their respective countries, Switzerland and the UK, and so 20A-EU1 had a head start by being in a very mobile population with quite a number of contacts. The first variant of concern was defined and reported just before Christmas, the B117 identified in the UK. And this variant of concern was spreading very fast, taking over first in the UK and then in all of Europe. And we looked at the Swiss data, so at the sequencing data, aiming at quantifying what is the transmission advantage of this variant. And so as you see here in Switzerland, we first detected the virus in December 2020, and then by March 2021, B117 was the dominant variant. And based on this increase in frequency, we can calculate back the transmission advantage, which we estimate at about 35 to 46%, which is also suggested in that ballpark, the transmission advantage, by a number of other studies. So B117 is a variant of concern because of property 1, a higher transmission compared to the co-circulating strains. What we additionally do for our Swiss sequences, we link them to clinical metadata whenever available. So, for example, to data on if the person from which a particular sequence is taken, if that person was hospitalized. And so now what we can do is, for the time January 2021 until now, ask how many people were hospitalized with a B117 variant, what is the proportion among all the B117 infections, and what's the probability that a person not infected by B117 but another variant was actually admitted to hospital. In blue, you see the probability that a confirmed case with a B117 infection had to go to hospital. In gray is it for all the other variants. And what you see is that there's a tendency that the blue bars are higher than the gray bars, so the probability of hospitalization is elevated for B117 compared to the other variants. So we see in the Swiss data a tendency for an increased severity of infections. This is also shown and quantified in a number of other studies based on UK and Danish data. The plots which I show on this slide here are from our dashboard cough spectrum. The link is given at the bottom left of the slide, where you can in fact investigate those sorts of characteristics of different variants for different countries. We import data, all the data from GIS8 on a daily basis, and enrich it with metadata we have available for our Swiss sequences. So I invite you to explore this dashboard. To come back to the start of the talk regarding immunity required in a population for the epidemic to stop. A transmission advantage of say 40% of B117 together with assuming an R0 in 2020 of 3 would mean that population immunity is reached only once roughly 76% of the population is immune. Besides B117, there are currently 3 more VOCs circulating. First, beta, which was identified in South Africa and is altering immunity, so has VOC property 3, as well as gamma, identified first in Brazil, also affecting immunity. And then last but not least, Delta, which was identified in India, and their initial data in fact suggests that it's both more transmissible compared to B117 and is also to some extent affecting immunity. With our sequencing efforts in Switzerland, we monitor all those variants, and in fact in our sequencing consortiums, we've identified all 3 variants in Switzerland first. Then, since then, we monitor the prevalence of those variants, and for all 3 of them, we are roughly at around 1% stable. However, that doesn't mean it needs to stay like that. Currently in the UK, we saw a very rapid increase of Delta over the last couple of weeks, and also in the US, Delta is starting to increase in frequency. Thus, we are also closely following the situation of Delta here in Switzerland. I will now conclude with some final remarks. With this talk, my aim was to show you that combining epidemiological and genomic data is required to monitor a pandemic. First, line-less data like the confirmed cases give us an overview of how the pathogen is spreading in general through, for example, the reproductive number. Contact tracing data then allows us to obtain a local scale view of who infected whom. But only genomic data can shed additional information on large-scale epidemiological patterns and strain-specific characteristics. So phylogenies allow us to investigate between which countries viruses are circulating, and genomic sequences allow us to track the emergence and spreads of variants. And in particular, if we have, together with the sequences, clinical information for those particular patients, can we assess properly the properties of variants of concern. This brings me to emphasize the importance of global sharing of genomic data, which is currently done through GISAID, but additionally calling for the need to link the sequencing data to clinical metadata, which is not done widely. Last but not least, I want to acknowledge all those fantastic researchers who made the presented work possible. And I would like to thank you for your attendance and look forward to interacting and discussing further. Thank you.